Hi, my name is Frank, and I am doing this video on eigenvalues. Now, first let's define what an eigenvalue is. An eigenvalue is a special set of scalars associated with a linear system of equations, for example a matrix equation, which are sometimes known as characteristic roots or values. And we'll go over this a little bit later, and it'll be more apparent in the video. So first, some applications of eigenvalues. First off, they're mostly used in computer graphics, in the modern sense, and rotational and linear transformations also, mostly in computer graphics. So in physics, however, eigenvalues are more used in quantum mechanics, waves and oscillations, which we will go over more later today, and dynamical systems. So these three kind of embody the more practical applications of eigenvalues. Now, back in 1829, Augustin Louis Cauchy basically first came up with this method of eigenvalues via celestial mechanics. He studied the rotations of 3D spherical objects such as planets and stars, and through this math, he found three equations and three unknowns through this rotational matrix, which signaled to him linear algebra. And we'll go over that next with an example problem of what eigenvalues are and how to solve them. Okay, so given the problem, find the eigenvalues of the matrix 3, 2, 2, 3. We are first going to get it into the form of m, r vector, lambda, and the other r column vector. And we could write this as such, with our column vector being something like x and y on both sides. Now that we have it in this form, we could apply the identity. The determinant of m minus lambda times the unit matrix is equal to 0. And we're simply going to plug this in for m. We have lambda right there, and our unit matrix is the matrix 1, 0, 0, 1. So plugging that in, we get 3, 2, 2, 3 as our matrix. Subtract that from lambda times the unit matrix. Take the determinant, and we get 0. Simplifying this further, we're going to get 3 minus lambda, 2, 2, and 3 minus lambda as a matrix, which determinant is equal to 0. Now, to solve this, we're going to multiply these two, and then subtract the multiplication of these two. So we get 3 minus lambda squared, subtracted from 2 squared is equal to 0. Now we can factor this, and we get lambda squared minus 6 lambda plus 5. And factoring this, we get lambda equals 1 and lambda equals 5. So these are our eigenvalues for the matrix 3, 2, 2, 3. So here we're looking at an application of the example problem we just did of a mass spring system with 3 springs and 2 masses here. And these springs have a different coefficient. And we want to find the 2 eigenvalues of the system. So first we start off by writing down the equations of the system, and we find that it looks something like this, and this looks like a matrix. So we plug that into our matrix form, and we bring the m down here, we have our column vector with the double dots on here, the second derivative, and we bring our k outside on all these terms, and we have our matrix. And we also have our x1s and x2s here and here, which become a column vector. Then to solve this, we plug in a trial solution to get rid of these double dots, the second derivatives, and we find that on this side, the second derivative of this is simply the same thing as that, as long as you bring out an omega squared. So now that we have that, we can set m times omega squared over k equal to lambda. And since we have that, we now have the form that we were looking for, which means we can then apply the identity. The determinant m minus lambda times the unit matrix is 0. So now we plug that in, and we have our matrix minus lambda times the unit matrix is equal to 0. We simplify that to this equation right here, and all we have to do now is take the determinant of that matrix. So we multiply both sides and subtract, and we get this equation here. We can simplify this part down into that, and that all becomes lambda squared plus 9 lambda plus 11. Now, we can't factor that, but we can use the quadratic equation, which is this here. Then that becomes plugging in a, b, and c, which is a, b, and c here. We get minus 9 plus or minus the square root of 9 squared minus 4 times 11 divided by 2. Now, those are our values for lambda, since we have a plus and minus here. So, we can then say that the eigenvalues for the mass spring system are minus 9 plus root 37 over 2 and minus 9 minus root 37 over 2. Those are our two eigenvalues for the system here. Here are my references, and thanks for watching.